Welcome back, everyone, to the deep dive. Today, we're going to go deep on something that might sound kind of niche, but actually powers a huge part of our world: slurry pump design in abrasive mining.
Yeah, you don't always think about it, but when we talk about getting all those essential minerals out of the ground, things like coal or copper, iron ore, we're almost always talking about slurries.
Slurries, right?
Basically a mix of finely ground up material and water. And it's kind of the most effective way to transport these massive amounts of resources, from the mine to processing.
Okay, so let me make sure I get this. We're trying to move tons and tons of rock and ore. Doing that as dry material, I imagine, would be a logistical nightmare, right?
Oh, absolutely.
You'd have endless conveyor belts, dust everywhere, but turning it into a slurry,
Yeah.
essentially making it a thick liquid, makes it flowable, right? Makes it much easier to move around. But then there's the catch. This liquid we're talking about, it's not exactly gentle.
Right. It's packed with super sharp, gritty particles,
Yeah.
not easy on the equipment.
No kidding. So this is where it gets really interesting. We're essentially talking about pumping a fluid that's constantly trying to sandblast the inside of your equipment.
Exactly.
These abrasive materials, think sand, sharp rock fragments, all that are incredibly destructive to regular pumps, the kind you'd use for, say, plain water. So break it down for me. What kind of damage are we talking about? What does this sandpaper in liquid form actually do to a pump?
Well, first off, you've got the constant friction and impact just wearing away at the pump's insides. We're talking about impellers. Those are the rotating parts, kind of like propellers that push the slurry along. Then there are the casings, which hold everything together, and seals, which are vital to prevent leaks. Over time, all this wear and tear means the metal gets thinner, you get cracks forming, leaks springing up, and the pump just can't generate the same pressure anymore. Ultimately, it leads to total pump failure.
And I imagine in a mining operation, any downtime is a big deal.
Absolutely. It's a 24/7 operation. Anytime a pump fails, it means lost production, and that translates directly into money lost.
Ouch. Yeah, that makes sense. So obviously, a regular water pump just isn't going to cut it in this scenario. That's where these specialized slurry pumps come in, right? They're designed specifically to withstand this constant beating. So what we want to do today is really unpack what makes these pumps so tough. What's the secret sauce, the engineering behind their ability to survive in these brutal conditions?
Exactly. So we'll start by digging into the specific challenges of these abrasive environments. Then we'll look at the core design principles that make these pumps so resilient. We'll even take a look at a real-world case study to see these principles in action. And finally, we'll discuss the key factors you need to consider when selecting and maintaining these crucial pieces of equipment.
Sounds like a plan. Let's dive in. First up, just how demanding are these abrasive environments? Well, we talked about wear and tear, but what are the specific ways this damage happens?
So there are three main wear mechanisms in abrasive slurry pumping. The first is abrasion. It's basically a scraping action. As the slurry flows, those solid particles are rubbing against the pump's surfaces, and that gradually wears away the material. Think of it like you're rubbing sandpaper on metal. Eventually, you'll start to see that metal disappear.
Okay, yeah, that makes sense. Constant friction just wearing away the material. What's next on the list?
Next is erosion. This happens when the slurry is moving really fast. Those particles hit the pump with a lot of force, and that actually blasts away tiny bits of material. Imagine a high-pressure jet of water mixed with sand hitting a surface. Over time, even really tough materials can be eroded away. So while abrasion is more of a constant rubbing, erosion is more like a series of high-speed impacts.
Gotcha. So we've got abrasion, the slow and steady grinder, and erosion, the more forceful hitter. What's the third element in this destructive trio?
Right. The third one is corrosion. This one's not strictly a mechanical wear issue. The liquids in these mining slurries often contain chemicals that are corrosive.
I see.
And these chemical reactions essentially weaken the pump material at a microscopic level. It makes them more vulnerable to both abrasion and erosion. So in a lot of real-world scenarios, you've got all three of these working together: abrasion, erosion, and corrosion, all ganging up on the pump. It's not just one thing, it's a combination.
Okay, so we've got this triple threat. Honestly, it's hard to imagine anything holding up under that kind of constant attack. So what's the impact of all this wear and tear on the pump's performance? It's not just about it failing completely, right?
Right. The effects can be a lot more subtle at first. As the parts inside wear down, the pump loses efficiency. It needs more energy to move the same amount of slurry. That means your energy bills go up and your operating costs increase. You'll also probably see a drop in pressure, which affects the overall flow rate and throws a wrench in the whole mining operation. And of course, in the long run, the pump's lifespan is shortened, which means more frequent replacements and more downtime. It's a cascading effect.
It all adds up. So I'm guessing regular steel just isn't tough enough for this kind of job.
Yeah, you hit the nail on the head. Standard steel, it's great for a lot of things. It's strong and cost-effective. But in this case, it's just too soft.
Right.
It can't handle the combined forces of abrasion, erosion, and corrosion that we see in these abrasive slurries. It would wear out super fast, leading to way too much downtime, and maintenance costs would just go through the roof.
Okay, so if standard steel isn't the answer, what are these heavy-duty pumps made of? What allows them to stand up to this kind of abuse?
This is where the science of materials gets really interesting. We're talking about two main types of materials: high chromium alloys and advanced ceramics. High chromium alloys, as the name suggests, have a high percentage of chromium. This makes the surface really hard, which gives it excellent abrasion resistance. And it also forms a protective oxide layer that helps fight off corrosion, especially in the harsh environments you find in mines. These alloys are like the workhorses for abrasive slurry applications.
And what about ceramics? When I think of ceramics, I think of things that are kind of fragile. How do they hold up in these tough conditions?
I get that. People often think of ceramics as being brittle, but the advanced ceramics used in these pumps are engineered to be super wear resistant. They can actually handle abrasive conditions much better than most metals. Now, they might be more susceptible to damage from sudden impacts, but their resistance to constant grinding and abrasion is amazing.
Interesting.
Choosing between high chromium alloys and ceramics really depends on what kind of slurry you're dealing with. You have to consider the size and hardness of the particles and the operating conditions of the mine itself.
It's all about finding the right tool for the job. So these specialized materials are the first line of defense against the harsh reality of abrasive mining. Now let's talk about how these pumps are designed. It's not just about using tough materials, right? The design itself must play a huge role in making them durable.
You're absolutely right. The material is crucial, but the overall design is equally important for maximizing the pump's lifespan and efficiency. So we've talked about high chromium alloys and ceramics, but let's go deeper into the design philosophy.
Okay, I'm all ears. What are the key design elements that set these pumps apart from standard industrial pumps?
One of the big things is robust structures. They often have larger impeller diameters. Now, for a given flow rate, a bigger impeller spins slower, and that slower speed directly reduces the force with which those abrasive particles hit the pump's insides. That really minimizes erosive wear. Larger impellers also tend to have wider passages between their vanes.
Wider passages, okay. Why is that important in these situations?
Well, wider passages let the slurry flow more freely. It prevents bottlenecks and spots where particles could get stuck and cause more wear or even blockages.
Makes sense.
This smoother flow also cuts down on the grinding action that happens when particles are squeezed through tight spaces. It's all about designing the pump to put up less of a fight, giving those abrasive particles more space to move through without constantly hitting the insides. So the benefits of these robust designs, larger impellers, wider passages, are twofold: increased efficiency and much more uptime. Fewer clogs, less internal grinding, all that adds up to fewer interruptions and longer periods of continuous operation.
Yeah, it's all about working smarter, not harder, right? So it's not just brute force with super hard materials, but also clever design principles that minimize the abrasive action happening inside the pump. You also mentioned something about optimizing flow patterns. How does that contribute to the pump's longevity?
Flow optimization is essential. By carefully engineering the shape of the pumps inside the impeller vanes, the volute, which is the spiral casing around the impeller, and the inlet and outlet passages, engineers can reduce turbulence and create a smoother, more laminar flow.
Right.
Turbulent flow is chaotic. It creates areas of high velocity and pressure fluctuations, which can really accelerate erosion and wear. Smooth flow, on the other hand, reduces these destructive forces, minimizes energy loss from turbulence, and, really importantly, reduces the need for repairs. I heard a great quote from John Carter, who's been an industrial pump engineer for 20 years. He said, "Flow optimization is the unsung hero of pump longevity."
I love that.
It's not about forcing the slurry through, it's about guiding it smoothly to minimize the damage it can do.
That's a great way to put it. Now, to make this all more concrete, let's look at a real-world example. You mentioned a case study in the Australian outback. That definitely sounds like a challenging environment.
Oh, absolutely. Picture this: a copper mine deep in the Australian outback. You've got scorching temperatures, dust everywhere, and a really abrasive copper ore slurry mixed with super corrosive water. The standard pumps they tried using were failing constantly, leading to nonstop maintenance headaches and huge losses in production. The sharp ore particles were acting like tiny cutting tools, and the corrosive water was making everything worse. It was a perfect storm of challenges that standard pumps just weren't equipped to handle.
A recipe for disaster. So how did a custom-designed slurry pump solve these specific problems? What were the key features that made a difference?
They brought in a pump that was specifically designed for those conditions. It had an impeller made from a high chromium alloy chosen for its ability to handle both the intense abrasion from the ore and the corrosion from the water. The casing was reinforced to take the constant beating from the heavy slurry. And importantly, it had extra large internal passages to prevent clogging and was designed with optimized flow patterns to minimize internal wear from turbulence. Every part of this pump was tailor-made for that mine.
And what were the results? Did it actually improve the mine's operation?
Oh yeah, the results were impressive. The mine saw a 40% reduction in downtime caused by pump failures. And the lifespan of the custom pump more than doubled compared to the standard models they had been using. That meant lower maintenance costs and a much more consistent and predictable production output. It really proved the value of investing in specialized slurry pumps that are designed with a deep understanding of the challenges specific to abrasive mining. What might seem like a high upfront cost for a specialized pump turned out to be a great investment.
That's a fantastic example of how smart engineering can make a huge difference for a company's bottom line. Now, for anyone listening who might be facing similar issues with abrasive slurries, what are some key things to keep in mind when selecting and maintaining pumps in these tough environments?
There are a few things that are absolutely crucial. First off, you need to really understand your slurry. What's the size range of the particles? How dense is it? Are there any corrosive elements in it? Once you have a good understanding of your slurry, you can start matching it to the right pump materials. For very abrasive particles, high chromium alloys or even advanced ceramics might be the way to go. If you're dealing with a thicker slurry, wider impeller passages are key to prevent clogging. And don't forget to figure out your required flow rate and pressure. You need a pump that's powerful enough, but not overkill.
So it's all about knowing the specifics of your operation and then choosing the right pump for the job.
Yeah.
What about once the pump's up and running? How do you keep it running smoothly and reliably?
Regular maintenance and monitoring are essential. That means routine inspections to look for wear and tear on the impellers, seals, and casings. Look for signs of thinning metal, cracks, or excessive wear. And it's really important to keep an eye on the pump's performance, things like discharge pressure and vibration levels. Any big changes could be early warning signs of a problem.
Right, catch it early before it becomes a major issue.
Exactly. Having a proactive maintenance schedule is really the best way to keep things running smoothly and avoid those costly, unexpected breakdowns.
That makes a lot of sense. Are there any specific operational practices that can help to prevent wear and tear and extend the lifespan of these pumps?
Absolutely. One common practice is to use wear-resistant liners or coatings on the parts of the pump that are most likely to wear down.
Oh, like extra armor.
Exactly. You can also adjust the flow rate to minimize turbulence inside the pump, which reduces wear. And a simple but effective thing is to flush the pump with clean water after each use, especially if you're dealing with a really abrasive or corrosive slurry. That helps get rid of any leftover grit or chemicals that can cause damage even when the pump's off. In the long run, the best strategy is to invest in high-quality pumps that are specifically designed for abrasive service and to combine that with a solid and proactive maintenance program. That's the key to maximizing pump lifespan and minimizing operating costs.
It's all connected. Well, this has been a really insightful deep dive. It's clear that slurry pump design in abrasive mining is much more complex and important than you might think.
I agree.
It's a fascinating blend of material science, fluid dynamics, and the realities of working in really tough environments.
For sure. When you get it right, slurry pump design isn't just about moving stuff around. It's a fundamental driver of profitability and efficiency for mining operations all over the world.
So to recap for our listeners, we've explored the intense challenges these pumps face, the importance of specialized materials, the need for robust and well-designed pumps, and the real-world benefits they can provide, like we saw in that Australian Outback example. And we've talked about the importance of selecting the right pump and keeping up with maintenance.
That's right. And taking a step back, I think understanding this complexity highlights the incredible engineering that goes into extracting the raw materials that we rely on for so much.
Yeah. It's a reminder that even these seemingly ordinary pieces of equipment play a vital role in our world. So the next time you see a product made from copper, coal, or iron ore, maybe think about the slurry pumps that helped get those materials out of the ground. And for those of you working in these industries, I hope this deep dive encourages you to think more about your specific slurry environment and how the right pump design can impact your operation and your bottom line. Maybe it's time to take a closer look at your pumps or talk to some experts.
It's definitely worth considering.
Thanks for joining us for this deep dives. We'll see you next time.